Okay, let's do it. All right, so welcome to the May 2022 Denver Erlang Elixir meetup, live in person and online. We're everywhere. Oh, come on. And we're recording, as the lady said. So if I remember, I will upload this on YouTube, if that's okay. What are you doing tonight? So I'll do a few announcements. We'll have our speaker. We'll have the opportunity for a little show and tell. And then we'll do online virtual hangout. And then I'll go by Mark and Dr. Pepper.
Dinner.
Okay, deal. Show and tell. So when I say show and tell, what do I mean? Do you have a side project, question at work? Hey, there's a thing I discovered. Hey, I'm having this problem. Share it with the group. It's not even really lightning talks, but just we can chat a little bit about a tech problem. If you have a little thing, great. Keep it short. If you don't, we'll move on, and then we'll just have social time. Okay. So who are we? We actually have a few organizers tonight, which is pretty great. So I saw Jeff and Dylan. Jeffrey and Alexandra, I think, are busy this evening, but the five of us try to keep this thing going. And I'm trying also to bring back the Denver component to actually get some people turning out. So as glad as I am that Mark is here, I would hope that other people will hang out with us. However, for the foreseeable future, I'm going to keep the online part because we great speakers like Bryan, who, as much as he loves us, probably does not want to fly out here just to speak. And our budget doesn't really afford that either.
You all have an awesome airport. It is like super cool. Every time I'm in the Denver airport, I'm like, that's the way you build an airport.
Like, yeah, it's
The
like
horse is terrifying.
The Taurus is terrifying. You're not wrong about that. Okay, so how do you contact us? So we post all of our meetups at meetup.com. We have a channel on the Elixirlang Slack, but really that is just a front door for our own Slack, which is Denver Beam. That is free to join. There's a link in the top of the Elixirlang for you to join it. And the reason being is that the free Slacks, both the Erlang and Elixir, tend to roll over pretty quickly. So we lose the scroll back, whereas the little Denver one, that sticks around forever because you've got like 10,000 messages. So it sticks around longer. But anyway, if you've got local things or stuff about the meetup, that's the best way to track us down. Okay, so quick shout out to our sponsors, Pay It Off, who are paying for the Zoom and the meetup. And now Blinker, once again, who is giving us this lovely, amazing conference room for me and Mark to hang out in. So eventually we may get beverages and food again, but we need people to show up first. So in the meantime, we'll do some Zoom and meetup. All right, does anybody have any general announcements? Okay, I am going to buy Mark a burger afterwards. So if there's anybody who is in town and wanted to go out for food afterwards, we're planning to do that, hopefully. All right, then every month we also ask the requisite networking questions. Is there anybody hiring?
We're kind of almost always hiring. There's not a spot right now at HCA Healthcare on our team at this moment, but in 2 weeks, they're, it's a big company, and so there's always interesting spots popping up on the various teams and Elixir. So if you all dig what you see in some of the talk tonight, then keep us in mind. And we do have remote folks like Brian Paxton. He comes to Nashville all the way from Memphis. So so remote is a thing.
You guys are in different time zones, aren't you?
Central. Yeah. But I think Paxton, you're central too, right?
Yep. Yeah, it's only 3 hours away from
okay.
from Hunter.
It's a long 3 hours. It's a painful 3 hours, but yeah, it's the same time zone, just barely.
Great. If you could be so kind, if you're serious about that, if you had a link to your jobs page, then I can put that. We have a Slack channel where we put job stuff, and then
what I can do is I can just ping you the minute that there is actually a spot.
Even better.
And I'll just hit you on Twitter. Yeah,
perfect. Yeah, and then I'll pass it along.
Awesome.
Anybody else hiring?
Sales Lab's also hiring anywhere in the US. Generally, I mean, we end up hiring a lot of people that have other experience and haven't done Ruby yet. So if you've actually done Ruby, yeah, we'll be even more interested. But
Sorry, is it a Ruby position or an Elixir position?
you would end up. Sorry, did I just say Ruby over
You
and over
did.
again?
You said Ruby a couple times. So I was a little confused.
Oh
there.
my word! I meant Elixir the whole time. We end up hiring people. Often they come from a Ruby background.
Okay.
Yeah, well, we have Ruby and Elixir at Salesloft. Depending what team you're on, you can have a preference, but you'll end up writing some Ruby and some Elixir.
Cool. All right. Again, if you have any job links, I will happily pass those along. So for people who might be seeking.
So I DM you on Meetup.
Yes, that's fine.
Okay.
You can put it actually in this chat because I can I get a copy
Cool.
after the meeting, so I can just copy it over into our Slack too, or
I'll do that now.
the other facilitators can grab that if they have a moment. That'd be great.
Thanks.
Anybody else? All righty. Anybody looking perhaps?
Yeah, I'm looking. So if you need a Erlang Elixir person that doesn't know a lot of Ruby, I'm that guy.
You came to the right meetup. All right.
also
I will
looking.
refer you to the aforementioned people who are looking, or sorry, hiring.
I'm also looking. I have no Ruby knowledge to speak of, and anything I did in Python is functional, so it's probably not performant in any way because I'm just trying to write Elixir in Python, really.
Wow, that sounds challenging, but interesting. So, all right, cool.
I'm also in the looking boat, but I'm much more based in Ruby, so I'm trying to transition into Elixir. So
All right. Yep.
Nice.
You're not alone, as you can tell. So cool. All right. Well, we'll try to, and just to let the people who may not know, we have a jobs, I think it's jobs channel on our Beam Slack. So we keep job postings there. And like I say, because it's slow, low volume, that stuff sticks around for a long time. So it's useful if you want some leads, and then people are probably more willing to make introductions because they're like, hey, I met you on that infamous, notorious Denver meetup. Anybody else? All right. It's my monthly plea. Speak, please, anybody. So if you have an interesting topic that you would like to share with the group, or you know someone who is dying to share with the group, because we're online, you can do this from pretty much anywhere. We would love to have you. Our only requirement is we'd love it to be Beam related, or FP actually. I'm going to make that exception because I think I was talking to Bryan before, and I think there's some interesting other functional languages that people would be interested in learning a little more about, especially if we could compare and contrast them to our old Beam friends. I think that'd be interesting too. So anything in that space. Also, if you're just new and you want to try out talking, we have organizers who will happily coach you. So reach out to us in the aforementioned areas, and we would love to get you on the schedule. All right, finally, without further ado, I introduce the infamous Bryan Hunter, who's going to be talking about Waterpark actors and distributed actors and the pandemic. And he will explain and introduce himself because he knows much more about that than I do. So I will stop.
Alrighty.
Hand it over to you, and you can illuminate us with.
Let's see here if I can
Yeah.
find my Zoom controls. I dropped from 3 monitors to 2 just then, and my world went weird. So okay, I'm finally back, I think. So and okay.
All right, we've got a third.
Oh,
more-
I'm sorry. I'm gonna have to
now.
quit and leave because of security. I'll be right back.
Okay, we'll wait here. I'll stall. All right.
Happens every time.
Yep, it does. It's almost, oh, I have to share my screen. You know, I didn't do that thing. I didn't push that one button. Yeah.
be fair, Apple totally ambushes you with that. It's like, oh, I got a shiny new MacBook. And it's like, oh, I haven't used Zoom on this thing.
It's a true story. And he just got a shiny new MacBook. So
Yep.
mhm.
Yes.
For us.
Yeah. We have local people, but we have people from elsewhere too. So
Alrighty, sorry about that. Had to go through the allow sharing thing. That's odd. I don't know what happened on this. Oh, I guess I had a new version of Zoom. Anyway, alrighty. So I think I could probably share now. And let's see. Yay. Can you all see?
it's good to me.
Yeah, we can see that.
All right. Okay, cool. All righty. So this is a talk that if any of you have seen this, if you happen to be at Strange Loop last year, this is very similar to that talk, but the difference here is we can stop at any time, and as you all have questions, and we can just take whatever format you all want to with this. And so there might be interesting things where you just want to wave the flag and say, hey, tell me more about that. And if it's coming up in a few slides, I'll say that. And otherwise, we can just stop and talk about that. But so welcome. This is Waterpark Distributed Patient Actors versus the Pandemic. And as the introduction, I'm Bryan Hunter out of Nashville, Tennessee, and one of the co-organizers of NASH FP, and which I hope to see you all on the fourth Tuesdays of any month. We always meet via Zoom, and you can find us at nashfp.org, and you'll find the Google group and the Twitter and all that from there. But so this talk, it's a real joy to be here because I'm able to talk about my team's research. And not always does research lead to a product, but this research led to a product that has a pretty unusual architecture, and it's out doing good in the world. So, and at HCA, I'm an enterprise fellow, and HCA is big. And I don't know if everyone on the call or who else is familiar with HCA, but to kind of give you a sense, 186 hospitals are fully owned and operated by HCA. So these are not, just managed or anything along this line. They're fully owned by HCA and operated. And there are 2,000 surgery centers, freestanding ERs, and clinics at HCA Healthcare. So, and a lot of folks work there. I've got 275,000 colleagues, and those people can all hit me on, I guess, WebEx Teams, and they can hit me on email. And so you can have a busy day at HCA when you've got something out there that people know about. So but this is the more important thing. And with 32 million patient encounters each year passing through, a lot of people truly depend on us getting things right. So back in 2017, I was presented with this research and development challenge within the enterprise integration team. So given all the data and the Erlang VM, what good could we do? And so if folks maybe have questions a little bit later, is like, why was that the challenge? We can kind of go into the history of that, but that was the challenge back early in 2017. So if we had all the data in their Erlang VM, could we improve patient outcomes? Could we help caregivers, so our nurses, our doctors, the staff? Could we help them do a better job? Could we help them day to day in their work? And could we give our hospitals a better footing in case there was a disaster or if there was a pandemic? And that's what ended up changing things from our research project, and it made it something else. We had some other goals as well. We had these secondary goals. First, could we deliver DevJoy? And so for me, DevJoy is being productive. If I can be at the office, get things done, and then have a chance of doing important work and that work be low friction, that's pretty much a delight. And so could we help developers around the org have DevJoy? And BizJoy, business folks tend to be happy when they have fast delivery times and lower risk and less uncertainty. And so that's this other part of the goal there. And if you have observable fault tolerant systems with stress-free failure models, then your ops folks are going to be full of joy there too. And so, and that experimentation proof research, it seeded several projects. There are quite a few neat ones out there, but the one we're going to talk about today is Waterpark. And so the name Waterpark, it's people a lot of times will ask, how did it get that name? And it came down partly to this idea that as we were building this thing, we knew we weren't going to just create another data lake. We weren't going to be just another copy of the data there that was sitting there and stagnant. And so, and the idea is you're going to have the system where the data is flowing through it. It's fast. You've had that dev joy, you have fun, and it's big. And so it seemed less like a data lake and more like a water park. And that name just sort of stuck and is this code name for it. And then as the product became a product, everyone kind of liked it. It made people smile. So that was kind of a nice side benefit. So to help patients and caregivers and our IT friends, we need to be up. And so we had to be highly available. Well, that was what we were told. Highly available was one of the goals, but that felt subjective. So highly available, what does it even mean? And so we designed from the start to be continuously available. So there's no downtime, and that's not subjective, that's objective. So if you have zero downtime, that's a known thing. And then another part of this was in an organization, if it's hard to get access to data that you need from teams, you know, this team has data and you want it or they have it, there ends up, it's hard to get, there ends up being a lot of data hoarding. And so we'll have everyone trying and clamoring to get a copy of everything. Even if they don't necessarily need everything, they'll want it. And they'll think, well, if I get a hold of it, I'll make sure and keep on getting a hold of it because if I need it later on, I'm stuck. And so, and that ends up spending, you know, you end up a huge amount of spend that comes off of that, off of, you know, just hard drives, if nothing else. And, you know, just all the redundant everything, and you can't keep things in sync and it's a mess. And so to prevent these data silos was a goal. And so if we make publishing and subscribing to data from popular tools, whatever stack, you know, people are in, the tools that they like to use, if we make it easy for them to come with whatever tool set they have and publish and subscribe data to us, and then ideally self-serve to us, then the hoarding stops. And then could we make a place for teams to create experiments? Could we make trying out new ideas fast, cheap, and low risk? And that that's one of the most special parts of having a platform like this that you're building, is to enable cheap experiments, because you could have looked at the beginning of Waterpark like a cheap experiment, and you could look at a lot of really brilliant things as these cheap experiments, and they start proving themselves. And then after a while, everyone depends on them. And so could we make that, lower that cost for this? And then finally, could we shine? Could we provide this example for the whole company, you know, all of the IT folks that are out building in the field and at corporate and so on? Could we create this example of how software can be built? And so we do a lot of that within the company. And then we share what we think is pretty neat out in the community as well. So let's get a view. So Waterpark, it runs on this cluster of servers, and the data comes in, and some of the data we just simply route. So this is what you think of when you think of integration. It's like, okay, people are going to send data and you're going to patch it on through. And that's sort of typical integration. Whether it's, you know, people would think of queues, you know, like RabbitMQ or Kafka or something like that. That might be the kind of model people are used to there. And then sometimes the data, we take the data in and we transform it and we change the shape of it into something that people want. And then some signals are generated entirely within Waterpark. And we do this by the data coming in. We're inferring knowledge constantly off of the data coming in. And this knowledge that we infer from all these disparate incoming streams are useful to people. And so that's another output of the system, is the things that have been pieced together entirely within the platform itself. So Waterpark, to kind of get a little bit of an idea of what it is, it's several things. And so we play a lot of bases. So it's an integration engine, it's a streaming system, distributed database, a content delivery network, a cache, queue, a complex event processor, and a function as a service platform. And so by taking Elixir and implementing the tiniest minimal set of features that we need from a cache or a queue, meant we didn't have to take a hard dependency on caches or queues. So interesting thing, Waterpark doesn't use a distributed database like React or Cassandra. It is a database. It is a distributed database, and it's a distributed RAM-based database. And so each time we looked at these tools, and we said, investing a few months in building a tailor-fit subset of the features that we truly needed lets us avoid these dependencies. And dependencies, even if they're free, aren't really free. And as a result of this, our deployment and failure models, they're our own. So we don't take on the patching cycles of things like Postgres or Kafka or anything. We use these things, but we don't depend on them. And we publish things to those other platforms that we were mentioning, but we don't depend on them for our uptime. And so this has been a key to us having zero downtime since we've gone to production 18 months ago. So we have Carl Sagan here. And so as virtuous as wheel reinvention can be, inventing the universe, it's a bigger job. And so it's important to distinguish between the two. Are you reinventing the wheel or are you reinventing the universe? And so we didn't want to build a universe from scratch. We didn't want to bake the apple pie from scratch. We didn't want to go that far. So for Waterpark, what that meant is we didn't reinvent hardware. And so we chose simple one-use servers. And we picked these boxes with onboard disks. And so they have no shared storage. These are basically simple commodity boxes. They're just 1U pizza boxes and with no special anything about them really. And so we expect these servers to fail. And we did everything we could to make sure that when a server fails, it was just that server that failed and the server next to it wouldn't fail, or the rest of the servers at that data center wouldn't fail. And so one thing to hear is on other R&D projects that are going on related to nerves, and possibly if I reach back out about jobs that are going on that are popping up at HCA, there actually might be a chance where you would be inventing hardware. And so we're partnering, there's a group spinning up alongside Waterpark around device integration. And so there are interesting things there. We're taking a big look at nerves there for interesting things, but that will be, again, pure research and development to begin with. And all right. And we said, okay, we're not going to write an operating system either, because you have all these things and that's a lot of stuff to build in. But what we did choose was we didn't go with just Linux. We chose this unconventional operating system of the Erlang VM. And so on a single commodity server, we run millions of actor processes. So massive concurrency out there on the cluster. So we really are running millions and millions and millions of processes. And these processes, they're auto balancing across our cores. And we get soft real time without having to think about it. And we never have to think about memory locks or threads or any of that icky stuff. We're really taking advantage of this operating system, Erlang VM. And talking to an actor that's running across the cluster, it's as simple as talking to a local actor. There's no difference other than physics. It's a little bit slower to talk across the country to an actor than it is one that's on the same server. But other than that, it's the same thing. And these are all things we get for free out of the Erlang VM, because the Erlang VM, it's a special purpose operating system. And its special purpose is to make sure that Erlang Elixir code runs flawlessly and as efficiently as anything anywhere. So it's full on built around the actor model, and that fits our needs. So if we go back to the actor model, back Carl Hewitt and crew back in 73, they introduced this model of concurrent computation. And this was inspired by physics. And you'll have other ideas that are playing around in the same space where their model was around cells and biology. But, so this was a lot of people having similar ideas, and it was all based on the way that the world works and thinking about those models of concurrency. And so in this model, actors are the fundamental element. And so you're basically actors. They can receive a message, and when they get a message, they can make local decisions. They can create more actors. They can send more messages, or they can determine how they're going to respond to the next message that's received. And so this primitive, this is interesting to look back, and then as we understand OTP and Gen servers and all the cool stuff that Joe and Robert and Mike built, and then Jose built upon, all these things, are right there, right in our toolkit every day. So to remove some magic, and so there's some folks that are coming from Ruby and maybe haven't dug deeply into the Erlang VM. They like the language and they like the way that the language feels. So we're going to take a little bit of a tour of the Erlang VM and its actor model and just some of the magic on this primer on the Erlang VM actor model and the process model. So every actor has some props. Every actor process has its own dedicated memory. And so we'll start off here with this dedicated, isolated, share nothing memory. And it starts off really little. You got this 2K on a 64-bit system. And inside of that, we have a stack and a heap. And our actors, they run, and as they take in messages and they build up their state, it grows, and the memory grows following the Fibonacci series. So it grows and grows and grows, but it's not just the same chunk each time. And then when it grows and you're no longer using that memory, each actor process also gets its own dedicated garbage collector. And so this is a really cool thing. And so if you're coming new to the Erlang VM, or if you're coming from other stacks, this might not be something you bumped into yet, but every process is garbage collected independently. And so we've got these thousands and thousands of processes. We got thousands and thousands of little GCs going on. And so, and you think about this is the memory model that we just mentioned, how you got this functional language. And so in functional languages, immutability is a thing. And so we have this place where you can't mutate state. All the languages are going to run on this VM are functional. And so there's also no shared state between those processes. When we're looking at that memory, if you remember, I mentioned isolated. And so the memory of that process can't be touched by any other process. And so if you're going to be a garbage collector, this is a place to be the garbage collector. It's the super easiest job. You go through, you can't mutate state. Once it's been set, it's set. Nothing's going to be reaching in. So you don't have to think about like shared memory and all this. Just awesome place. And so as a result of that, these GCs end up being really efficient. And since they're done at the process level, they're tiny. And these buttery smooth GCs that are going through, we end up with the opposite of what you'd end up on the JVM or the CLR or something along that line, of where when the system gets really, really busy, you have a stop the world garbage collection. You have a stop the world GC. Well, you just wouldn't have that on the Erlang VM. Each one is going to be independently GC'd. So that's a really cool thing. And then one of our other props, this one's fun, the mailbox. And so it's a good thing that every process gets its own dedicated mailbox, because that's the only way that process is going to be able to talk to the world. So again, the memory is isolated, so I can't reach in and see the memory of some of the process unless I send that process a message and say, it's like, hey, I'd like to see your process. Give me, I'd like to see, some of the values within your state. And this idea, it extends on even to file IO. And so if you poke around and you look down in the guts of how the file server works, so this is one that it might take a while to dawn on, but it ends up looking a whole lot like the idea of the IO monad over in Haskell land, because you have the only way you can really reach out to do anything is to send messages, and even side effects are you just sending messages to something that's been dedicated as the thing that's going to actually touch the disk or touch the network, and those bits being written in C, but you're sending messages to those things that look to your process just like it's another process out there. So I think that's pretty interesting. And then we have links and monitors. And so we can tell the Erlang VM that we want to know immediately if some other process on the same server that we're on, where our process is running, or anywhere across the cluster, if it crashes. And so a link is the full Thelma and Louise situation of where you have this death pact. You know, it's a bidirectional death pact. If I link to you and that process dies, I die. Or if we're linked and I die, that process dies. And then there's the less intense view of this, which is monitoring. It's more like reading the obituaries. And so I can monitor a process over here. And if that process crashes, I'm going to get a message in my mailbox that I can respond to, or I can look at it later and say, oh, that's sad, that process died. And then you can move on and deal with whatever you're going to do based off of that. And so these ideas here, this links and monitors, well, each one of these things really, but in particular, links and monitors, if you've wondered how supervision works, well, this is it. This is these primitives that we're looking at here are how all the goodies inside of OTP are built up. So these primitives were there. And then as these people took different approaches at writing out patterns on top of those primitives, you ended up getting supervision trees, you ended up getting gen servers, you ended up getting all sorts of neat things built up on top. But this is how it runs. So one other bit, while we're down in the guts of the VM, let's look at how scheduling works. So here we have a single CPU core, and we get a single Erlang VM actor process here. So we have this this CPU core, and we have a single scheduler that's going to then run the processes within on that core. Okay. So imagine this. So you got a CPU core, you got this scheduler up here, and each process is, you can think of a program really as a stream of operations rather than, you can think of it as a queue really, or something along this line. It's not a bunch of threads where they're all fighting the clock to say, give me some time. And as soon as they get it, they don't want to give it up. And there's all this battling and all this with thread context switching. But instead you have this near zero context switching cost of going from one process to the next, because that process gets to do 4,000 bits of work. So 4,000 reductions, used to be 2,000 reductions, but now 4,000. And chunk. And immediately after those 4,000 function calls or operations, or if it's waiting on IO, it immediately yields. And then the next process comes and schedules in. And there's nothing that one of these processes can do to get more than their 4,000 reductions. So everyone gets so if there's one guy in there calculating pi, and he's wanting to get to the last digit of pi, and he's gonna, oh, just let me, I'm almost there. I'm gonna get to the last digit of pi. The Erlang VM says, okay, well, I appreciate your enthusiasm, but I'm gonna give you 4,000 runs at the clock this time, and then I'm gonna give your buddy who's over here drawing a Phoenix live view page, I'm gonna give him some clock, and so on and so on and so on. And so as a result of that, you have no hogs. And you get the soft real time that happens. You get 2 CPU cores, you get 2 schedulers, and those schedulers are going to be balancing the processes across them, and you get this buttery smooth across 2 cores, and so on and so on. And so Waterpark, each one of our 1U servers has 56 logical cores, and so we one server would have 56 of these things doing like this, and that would all mean that we could do 56 things in parallel, but we can do millions of things concurrently, because, you know, of course the ideas are different. Concurrency is about how you structure your code, and parallelism is about it actually executing all at once. And so how does all that apply to healthcare? So we start off with this idea of digital twins of digital twin of the patient. So we're looking at gen servers or actors. We're looking at those as a digital twin that's going to represent the patient. So this is an actor process per patient and not just some database row per patient or some file stored somewhere or something along that line. This is a live running process. So typically in healthcare, a patient's represented as a moment in time snapshot of data. Whether this is HL7 data, which we'll look at in a bit. These are table rows or JSON or whatever on disk, and that's where it's at, and it's just sitting there. In most systems, they read this patient data and they perform work based on current values, and they flush memory buffers and they move on to the next data. And like the goldfish, they have no idea what happened the last function call that they were calling into. So in Waterpark, though, we're different than that. We're going to model each patient as this long-running patient actor. The patient actor represents and is dedicated to one individual patient. These patient actors run from pre-admit to post-discharge. And so it may run for weeks. And actually, it's guaranteed to run for weeks. And so if I stub my toe and I go over to the local HCA hospital, I go to Centennial Medical Center, as soon as I show up there, there's going to be a message that's as soon as the first message has been keyed into a system, there's going to be a message for me. And maybe they transfer me to the back into the ER, and maybe they send me off for x-rays. Each one of these things is going to be this message, but those messages are all going to be there for, so when I first appear, this patient actor that represents me is going to be there for a minimum of 2 weeks. And then every message after that resets our clock. And so it'll be 2 weeks from that next message that comes in. And so definitely long running. And people maybe are surprised by that, these gen servers that are up and running for weeks. So a patient actor is not limited to the data in the latest HL7 message that's come across either. And so it holds every HL7 message and event that led to the current state. So you might be thinking memory. You might be thinking that's a lot of memory. And so we do have to think about memory, because we're storing all the messages that come in for every patient in the enterprise, and at all these 186 hospitals and those surgery centers and so on. And but we're storing these messages compressed, and HL7 compresses well. And our gen servers, if there's no activity on them, we go ahead and let them hibernate. If there's nothing happening, and so this is a special thing that gen servers can do, basically helps them do a deep clean of their memory if they're not being used. And it's a little bit expensive if you are waking up and going to sleep, but we just set a timer on, and if nothing's happened with that patient actor for a little bit, we go ahead and let it hibernate. And we also have eviction policies. So if we had some outlier patient or something in the system, it wouldn't just spoil the fun for everyone else. We wouldn't run out of memory. And so when I mentioned that it holds every message and event that led to the current state, that could be thousands and thousands of messages. So this is based on this idea called the long shift. And so nurses, they often work these 12-hour shifts to provide continuity of care for patients and reduce the frequency of dangerous handoffs. And that idea comes into this eye chart here, but the important part is here. The 80% of serious medical errors are around miscommunication during the handoff and transitioning of care. And so when nurses are changing over and you're handing the patient off to another nurse, that's where the dangerous stuff happens. And that's where JCO says this is where 80% of the errors happen. And so what we want to do with Waterpark is we want to say, okay, patient actors are going to extend this long shift idea by providing continuity of care for our clinical systems. And so instead of having that goldfish memory, we're going to have this long shift idea on these, and it's going to give us better context and awareness of the full patient's visit. So this full visit awareness is going to allow us to perform real-time notifications and alerts based on days or weeks of events, maybe even if those events are separated by hours and hours. In the millisecond that the second event comes in, click, we fire an event. And so whether those events are transfers, drugs administered, lab results, or procedures. A little bit of a visual here to kind of make this a little bit more concrete. This idea of the patient actor. So here we have a facility with 2 patients. And so EMR, if you're not familiar with hospitals that are, this is sort of the systems that the electronic medical record, or the big systems where all of the clinical data flows in and out. So if you think of maybe like a big business software like an ERP system that maybe has warehousing modules and would have accounts payable and all that. Well, an EMR is basically the special purpose vertical software like that, but it's all around tracking things like orders and admissions and discharges and so on, and results, basically just medical things. And so in our EMR, EMRs tend to send this data. We'll see this arrow here that says HL7. So we receive patient events as HL7 messages, and we create a patient actor per patient to process the messages. And so up here, message flows over. Bryan Hunter stubbed his toe, came in, and was admitted. And so patient 1001, there I am. And another message comes in. And so they're going to give me aspirin because I'm whining a lot about my toe. And then another message comes in for some other patient. And so had we seen that patient on the cluster? Well, no, not yet. So we're going to spin that patient up. And then another message comes in. And it's like, oh, that's for 1001. We already have that patient out there. And as you see, patient 1001, this transcript is building up off these raw HL7 messages. We were able to infer meaning from each one that came across, what this all means, each one of those things. All right, so we've mentioned HL7 a bunch of times. And let's take a little peek at HL7. So here's HL7. Does that look fun? It's really, to be honest, it's not really a lot of fun, but it's valuable. And so to make this eye chart a little less of an eye chart, let's create some space in there, and then let's bold these things called segment headers. And so this is a message. If you were to look at the Wikipedia page on HL7, this is what you're going to see. You're going to see this ADTA01 message here. It has a patient ID, a Barry Klein sample, and you're going to see these observations of body height, weight, and so on. And so let's see, this is going to be the first place that we're going to see a particular thing of how Elixir and Erlang, how the Erlang VM plays in with this. And so to make our job easier, we're going to have HL7 in the bit syntax. It's going to come to the rescue here for us. So this first part, if we do a binary, use the bit syntax, and we can match across something like this. And we say, okay, our left 3 bytes are going to be MSH. Yep. And then we're going to say our next byte. So if you were to look at this file before, you'd have probably thought that, okay, this is a pipe delimited thing. But that's not quite right. So the 4th byte of this file says what the field separator is going to be. And so if we match here, we say, okay, it's a pipe, and we can come down here and we can say, we can also say that this character had better be a pipe. Those had better be the same thing. Otherwise, this is not HL7. And so, and then we have those encoding characters in the middle. So we could have actually done this. If this 4th character was an @ sign, then the field separator would have been an @ sign throughout the file, which is kind of nutty, but anyway. And so these other things in there, these are the other, are going to be the delimiters for separating like within a field, to break a field up into subcomponents, or lists of fields. So the tilde basically creates a list within that field. And so you have a repeating group. The little caret defines a subcomponent. Then we define the escape character is going to be a \, and then the ampersand is going to be if a component is broken up into subcomponents. And so you can think of this HL7 message here as a little tree data structure. And so you have all these nested things within things within things, a few levels deep. All righty. So if we were to look at these, and so there's a path syntax here called MSH -3 would be the way you would refer to this thing. And so this is going to be the sending application, megareg. So it's a registration system, I guess. And then the sending facility, where's it coming from? And the receiving application, who is this? What system is this destined for? app is this destined for and at what facility. Then we have the message date and the message type. So it's an ADT A01. And if you were in this, that's an admit message. And so you start picking up all these arcane weird things, and you can start looking at this and scan, and things start popping out like the Matrix before long, where some of it starts making sense. And we have a message control ID, the message ID here. And then we have the HL7 version. And so different versions of HL7 will have different depths to this tree, but they more or less look the same. It's just a higher version will have more subfields and so on defined, and more data types that are a little bit tighter. So that is, you can imagine that that's a mess to work with. And so I went from back in 2017, when I first came to this, I had never seen HL7. I'd heard of it, but I'd never actually seen an HL7 message. And pretty quickly in the research, it became the most important part of my day. And so what came out of that, worked with my colleagues, and we built out a library where we could parse this stuff. And so I built a really terrible first version of this thing. And then some of my colleagues, some of my peers, they took this thing and it got better and better, and we were using it for more and more things. And now it's open source. And so if you go to HCA Healthcare / and then Elixir HL7, you have this Elixir library that helps you deal with this with HL7. And so I thought that was pretty cool that we built this thing. And there's a phrase at HCA, there's a whole that you'll hear a lot about caring for the community. And there's a lot of community service work. And so this was actually just part of what we did. We were just raising all boats and then helping other folks out there needing to deal with HL7. Every week or so, I'll hear from someone in the community from some other company, and they're like, hey, yeah, getting good use out of the HL7 library, and they'll ask us about other things if we're going to open source. And it's like, well, maybe. And so different projects that we're talking about, different components inside of Waterpark, if y'all are interested in, and you'd like to see some of these things getting open source, we can start trying to prioritize parts of those as well. All right, so let's get a peek at what this HL7 library looks like. By the way, do we have any questions at this point?
Actually, a small one.
Okay, yeah.
So I have some at an Elixir conf. I was talking to somebody I think might have even been working with you, but they were talking about how the hospitals have different, like, because this is a spec, right? And it's not always correctly implemented. Do you run into that? Because this is all your hospitals per se, or?
Yeah, well, it's not consistent even within. So you think about a company that has 186 hospitals. You know, some of these hospitals are hospitals that were out there. There was something good about them that seemed to fit with what HCA was up to doing, and so they were a hospital that was acquired. And so they already had their EMR set up, and they were already configured a certain way. And so we're dealing with HL7 coming from lots of different EMRs. And so the big EMRs out there, you've got Meditech, there are different versions of Meditech. You have Epic and Cerner, you know, so all these different EMRs that are out in the world, we probably have them. And so the HL7 from one hospital might not look at all like a HL7 from another hospital. And so what we do in the HL7 library is we try not to get too caught up in what a data type should look like given this version of HL7, because it's not really, you know, if we were creating HL7, we would want to validate it and make sure it was right. But if it's in the world and it's really what the EMR is sending, it's not really our place to say, oh, that's not really valid. We're not going to take that message, because I mean, it's how the business gets done. It's how patients get transferred from rooms. And so we go ahead and say, okay, whatever is there, we take. And what we will try to do is the data comes in, we'll try to extract meaning out of that data. And a lot of times we're doing it on a per EMR basis, and we could do it also on a per facility basis, but we have all sorts of basically, and we'll look at this as we get into the event handlers later on, about how as data comes in, we can inspect that data, and then we can have different strategies for different EMRs or for different facilities and so on, so that maybe this bit of data that well, actually, let me move a couple of slides forward, and then I'll.
I feel like I got ahead of you. Sorry.
Oh, not at all. That was good, because this will hopefully they'll make it a little bit more concrete here, what we're about to see. So the IEX, here we are in Elixir, and we're going to say message is equal to HL7 message new of this HL7 text, and we're basically talking about this slide here. And so we newed up an HL7 message off that text. And then we can say things like HL7 query new. We can say, give me a query getting part of AL1 3.2, and it's going to be aspirin, because we were down on AL. Oops, sorry about that. So we're over on the AL segment, and we're at 3, and then we're at the second component within that. Okay, so if you were looking for allergies, and at 1, on this HL7 message, the friendly name of the drug is over here in 3.2 that they have an allergy to, but it might be somewhere else. It might be, maybe even you might even be able to clearly say it's in the wrong place, but it doesn't matter. It's in the wrong place. It's still, that's where it's at. And so for that EMR and for that hospital, we would say, okay, well, even though that's not really where it ought to be, that's where it is. And so we would extract that meaning a different way at that one facility, and we'd extract it from this place, from this AL1 3.2 at this facility, and so on. And as we're extracting that knowledge, then the patient actor would have this knowledge that had been extracted, and you wouldn't have to think about the source that it had come from. So everyone is being normalized. The parts that we're going to infer from the data coming in, we're going to try to normalize that so we have the same attributes. It doesn't matter which facility or which EMR that the patient's at. And there are a few cases where it is tough, because maybe they just don't capture that data on a particular EMR or a particular facility, and so and then you just deal with the gaps, and you won't be able to get from A to B sometimes, but we have the tools, and we have this malleability here of this dynamic language that makes a lot of the stuff easy. And then the HL7 library here that we have, it also is very loose in the way that it pulls things in. If something has a value, it's easy to get to. If something is not there, it gracefully says, well, it's not there. Okay, and so hopefully that filled in a little bit of that blank of how we deal with the disparate systems. Okay, and so we can move on from here. So we had lots and lots of research as we're going through. So the first part was the research of like, oh, I've got this HL7 message. How am I going to get something out of it? And then we moved on, and various problems came along. And we do a lot of reading on the team. And so there's a paper. So I don't know if y'all are familiar with papers we love, but this is a really cool, basically it's like a user group, but you read a research paper, and then someone will share the research paper at the next meeting. And we do a light version of this, or this becomes a component of what we do at Nash FP, where people take a paper and we'll dig into it. But here, this paper, scalable Bloom filters. Let's take a peek at what these are. So you have this probabilistic data structure, and it supports 2 functions. So this data structure, you can add items. So if you're thinking like a set, you can add items to a set, and you can ask if something a member of a set, right? But if you're adding every field in the world, your set is going to grow and grow and grow, right? And so here, your map set's going to grow and grow and grow. What this scalable Bloom filter does, it's a probabilistic data structure. And so instead of storing every value that we add into it, we're going to store a series of hashes that will be able to tell us. We won't be able to retrieve the item back out of it. We wouldn't be able to say, hey, Bloom filter, what all items have you added in here? We can't say to list, for example. But we can add things in, and then we can say, hey, have we added this member in before? And we're guaranteed with the scalable Bloom filter to never get a false negative. But we can get a false positive. So sometimes it'll say, hey, have I added this value in there? And it'll say, Yeah, I think you did. I think so, because it's all working off of hashes and basically flipping bits on and off. And so occasionally you'll have a collision, and maybe you flip the right bits. A different word would flip the same bits up. And so every once in a while you get a false positive. But you can configure that with the scalable bloom filter. Say, okay, what I want is I want to have say 99%. I want to maintain my false positive rate at below 1%. And with the scalable bloom filter, then what it'll do to make sure that happens, it will just grow the size of your bloom filter. Now, it's still going to be tiny compared to if you were actually holding all the values. And so if you were interested in this idea, here is, well, I'm just going to grab the rule book right in front of me, but you can, here it is. So this is an excellent book and walks through all sorts of probabilistic data structures. So let's see how we would use this inside of Waterpark. So we're back to this HL7 message. And so we've got actor patient 1000 bloom filter here. And so we're going to add, let's add a string to the bloom filter. That's the HL7 path, AL1 3.2 colon aspirin. And let's add an HL7 path of DG1 3.1 colon 78650, or basically this code that represents chest pain unspecified. Okay, and then let's add the PID 11.5 here, this zip code. And so in these strings, we're actually storing the path and the value to the bloom filter. Okay, and so we could go through and do that where we're walking through the terms. And on the left, we said path colon value, we're adding those to the bloom filter. And then over on the right, we're going to, those same terms, we're going to store just the term without the path. And so what do we have here? Is this clicking about what we're getting to get out of this? So on the left, or on the right, when we just add all the words just all by themselves in bare, this is going to be basically the foundation of a full text search. And then on the left is going to be an advanced search. And we're going to be able to support that both off of this idea of a bloom filter. And so we'll be able to do things like, is member of this bloom filter PID 7, 1962, so the birthday. True. So that is the birthday for this patient. And is member of patient 1000 bloom filter, Birmingham. And so this is a full text search because we didn't specify the path in this one. We didn't say the HL7 path. We just said, hey, is Birmingham somewhere in here? Sure enough. And then we said, is bloom filter SARS-CoV-2. It says false. It said false because COVID-19 didn't exist when we were doing this work. so here we are, we're busily down just doing research and having all sorts of fun and digging into things that are super cool and super useful. And instead, when this happened, we took the system that was pre-production and we had this mandate. In 3 weeks, you need to take Waterpark to production because there's a pandemic on. And another way of putting that would be in 3 weeks, you will never again be able to take downtime. So that leads us to continuous availability. And what this means is no unplanned outages and no planned outages. So we don't have patch weekends and we don't have downtime for deployments or anything like that. We have to always be running, and we have been running since we deployed. An interesting thing is, let's see, about 6 months after we went to production, we were looking around on the system and we found that there had been patient actors that had been up and running since we had first went to production. And so, and at that time we had done many releases and we had patched servers and all this. And we're talking about the system that is entirely RAM based. So on this cluster, it's entirely RAM based. And they're these running things in RAM that have been up and running for 6 months. And so you might wonder about how you got there. How did that happen? And a lot of it comes down to this idea of no masters, no single points of failure. And so let's look at some examples here, some anti-patterns. And so here we have a task router node and then 3 worker nodes. What we have here is we have a master. We have this task router node, and if it's down, then you're not really going to do any work at that point. You've you're down and no work is going to be happening in the worker nodes. And then here we have another anti-pattern. This is a really bad plan. So you have worker node, worker node, and shared storage, whether this is a database or some centralized place that you're going to put your data. And if the database is down for patching or it crashes or whatever, all those nodes are going to be stuck and they're going to be crashing too, and you're going to be pretty much down. So we wanted to avoid that. So let's look at here's in series, these roles in series is one thing that this is called. It's also called the N-tier architecture. You might have heard from way back in, I guess, the 90s. You'd have heard N-tier architecture. And this is a lot of times that would be broken up with web, business logic, and database. And it's also known as the worst high availability plan ever, because if any one of these is down, you're fully down. So if your business logic tier fails, it doesn't matter if your web server is up. All it can do is say, whoops. If your database is down, you're going to get a bunch of crashes and errors. And it's a whole big bunch of being down is what it is. And let's look at the problem. So if we have a component and it's 3 nines of availability here. So given a component with 3 nines availability, that basically means 8.8 hours of downtime a year. And that is about 8.8 hours more than we are allowed to take per year. And so that wasn't going to work. So let's look at this. If we look at these in series versus in parallel, if you line these up in series, you get 26.3 hours per year downtime. If any one of these components fails, then you're down, and that you've went from 8.8 hours to really bad. You're over a day down every year. But if you put these in parallel, these same availability components, and if you come into them and you can hit any one of them as long as one of them is up, if any one of them is down, you're okay. You're down to 32 milliseconds per year. Okay, so that's getting there. We're liking this 32 milliseconds a lot more than that 26 hours. So if we had 3, that's good. What would be better than 3? Well, how about 8? What would that give us? And then what would 8 give us if we put a way so that if we separate the chance of failure into availability zones? So the hardware on one side of this thing is completely separate. If the power goes out, the things on the left are going to be down, but the things on the right are not going to be affected by that. If the network fails, same sort of thing. So let's have this idea of availability zones. And then let's take this idea and say, okay, what if we spread this around the country? So we have Florida, Tennessee, Texas, and Utah. And so we start seeing our 9s climbing here. And so we start going way, way beyond what those 3 boxes in parallel gave us. And we're definitely not in the territory of the things in series. And so all of the design of Waterpark is around this idea of minimizing the single points of failure, trying to squeeze those out. Okay, so what do we do when things fail on a particular server or in state? So we've been talking about this idea of everything running in memory, and that's, there might be people flinching every time I say that, like it's only in RAM. And so process pairs. Let's talk about that. So process pairs was a technique used by Jim Gray in the design of the fault-tolerant tandem computer. So this process pairs idea was adopted early on in the design of Erlang. So here you have Joe Armstrong says, to be fault tolerant, nodes in a cluster must be able to detect other nodes crashing. Remember the links and monitors bit from earlier? Yeah. And they have to have sufficient data to take over for the down node. And users should not notice the failure. So how do we pull that off? So here we're back to our diagram of the Waterpark cluster with our data centers and availability zones. And I'm I'm over at I've stubbed my toe, and there's my patient actor that spun up on the cluster. So we're also going to have a read replica of me somewhere else at that data center and somewhere at each of the data centers. And so we're going to have a total of each patient is going to have 4 read replicas scattered across the cluster. And that's going to give us a few things. Does anyone have guesses on what we get out of that and what that's going to let us do? So there's the one that we're talking about right now about the idea of the process pairs. And so then, of course, instead of a pair, we've got these 4 buddies of the thing. So if this process, if the whole server dies, for example, or the process dies or the whole server dies one way or the other, and it is RAM, what's going to happen is that box is gone, and we know then to spin up off of that 1001 over at the on that B2 server, Florida B2, it's going to spin, and we're going to have a writer restored off of the memory that was in the Florida B2 server. Another thing we get out of that is locality. And so not only do we have this, so it's similar in a RAID hard drive where you get 2 things out of RAID hard drives. You get backups in case the drive fails, but you also get speed depending on how you set up your RAID. So we've done a similar thing to that here with the cluster. So we have these replicas. And so if you're doing a big bulk series of reports, or you're doing some sort of crawling on patients that are around the entire enterprise, well, you can be down here in Utah and do that. And the entire, all of the actors are actually, there's a full copy of them local here to you. And you're just hitting the read replica. So every patient is going to have a read replica at every data center. And so you get this CDN, as I mentioned earlier on that first early slide about the different roles that we play. All righty. So one question you might be thinking is like, okay, how did it know after it went on Florida A2, when Florida A2 went away, why did it show up at Florida A3? And why is that one over in B2 and Tennessee A4 and Texas B4 and Utah A1? Why those servers? How do we know anything about that? And so let's look at this, server hash rings. So if we define this hash ring, you can say hash ring new, we're going to add some nodes. We're going to add 8 nodes. And then we say hashring.key to node. We say actor key 1001. And it says S7. And it's always going to say S7. So given that hash ring, this is a deterministic function. So as long as our hash ring has those 8 servers on it, every single time that we pass in actor key 1001, it's always going to be S7. So we can count on that. Right. Let's look at another paper here. So rendezvous hashing. And so this is going to build upon our idea of our hash ring, of where you'd be able to go from this key maps to that node. And it's going to give us some clever extra goodies in here. Okay, so given a key, actor key 1001, each server is going to assign the key a score. Okay, so this key, so they all take this, and based on their local bits, so the hash ring is going to say each one of these nodes, you're going to get a score on each one of the nodes within the hash ring. They get scored. And so we're going to then say the server scoring the highest will own that key, or the node scoring the highest for our key is going to own that key. Okay, and so in this case, S7 is going to own, and that's how we got our S7 a minute ago, because it scored it the highest. Now, so it's there. What happens if our topology changes though? Now, if we were dealing with just a regular, like a p-hash2, Erlang p-hash2, and we changed our number of slices, well, everything would jog around, and that would be super expensive, right? And so, but here, even if we drop servers 2 and 3, well, 94 is still the high score, right? So it's going to stay at S7. And so we didn't have churn. Now, if it had, if say if we lost S7 here, that has the 94, then we would move over to S3 because it has the highest score then, right? And so on. But in this case, since we dropped two that weren't the highest score, that key did not need to be moved. And so as a result of that, we didn't have so much churn on the network. And so that is good. Okay, let's talk a little bit about topology. So we build up on this idea of these hash rings, and we're gonna say we're gonna have a hash ring at each DC. So we're gonna have a hash ring over here at Tennessee. We're gonna have one at Florida, Tennessee, Utah, and Texas. So we're gonna have each one of these. And if we take a value and get actor servers of a particular actor key, it's gonna say Tennessee B2 pop. And so there we were. And so this is, given our topology is stable, and everything is here, this will always lead us to the right spot of where that thing should live. Okay. Does this resonate as far as what we're getting out of this? This is powerful, spooky magic here, because what we wanted this globally consistent process registry, but that was too expensive. And I proved it was too expensive by doing it the other way. Early on in the R&D back in 2017, we attempted using, there are lots of things that were tried. And so that whole year was building proofs. We would take these 2 or 3 days to try out a technology. We would use some open source library that was out there. We would use some pattern that was there. We would implement a white paper. We would do, and so we would build things out. And we tried all of the different distributed registries, distributed process registries. And they would maybe work fine for a few servers and they would work fine for a few values, but we were intentionally torture testing things. And so I can show you a model here. So we have these blocks here that represented our data centers, and I've got, we got all these different mini data centers here. And so you could torture test these things by disconnecting the network, and then all of a sudden you have a partition there, or you yank the power, or you remove the hard drive by click, the hard drive is now out on this server, and so on. And so we could simulate all these failures. We could also simulate them just on the laptop inside of, just spinning up mini nodes and inside of Docker, and instead of, things on that line, we also had these physical models as well. And so we wanted to, and early on, a funny thing is in the dashboard for Waterpark, similar to that view where we had the 4 data centers and the servers going across, we had a button that we call crash. And so you'd select a server and you'd say crash, and it would basically do an Erlang halt. And so we'd intentionally just drop the entire Erlang VM just like on a button click, just to see how well recoveries happen and how processes migrated and so on. And so we pretty quickly learned that a global process registry is far, far too expensive. And so our solution, math. So we had these, the topology. So what we knew we had to do, or what we could do, is as long as we could maintain consensus on just the topology. So as long as everyone in the cluster, they didn't have to agree on where these million processes were, and they didn't have to agree on this key is over here, and all of them synchronizing that, and every time a process starts or dies or something, you would have to update your tables. We didn't have to do that. We just have to maintain consensus on one tiny thing, that little map of this data center has this hash ring, this data center has this hash ring, and so on. So that tiny amount of memory there, that's what we had to have consensus on. And so once we have that, then we can route to the proper local process registry, which is super fast and super cheap. So just the built-in Elixir registry. And so we took care of the expensive part by just using math, and then we do the last mile part using Elixir's registry. And so we don't now need this global process registry. So consensus, though, even on a little thing, is not easy. No, it's not easy at all. And so this brings us to another papers we love. Heidi Howard, distributed consensus revised. And so the idea is, so comes in and talks about Paxos. And so Paxos is this widely deployed in production system that's poorly understood, and it's heavyweight, and it's unscalable and unreliable in practice. And so that's Paxos, and a lot of systems depend on it, and they don't behave as well as we behave when the world's going badly. So we couldn't depend on Paxos. One is we couldn't understand it either, and then two is it would have been far too heavy for what we're doing. And so that quote is, we agreed with it, and we also had a similar story with Raft, which is ideas it's much lighter weight. And so we tried out every Raft library that was available on the Erlang VM, and then we made attempts at implementing the paper ourselves. And each one of these cases, you would end up in spots of where, when things went really badly on the cluster, Raft, it was just not fast enough. It couldn't deal with the churn that we were throwing at the cluster, or throwing at Raft, and it couldn't maintain consensus. And we'd end up in these deadlock spots, which was not good. So what we realized, though, and this talk by Heidi Howard at Papers We Love Conf 2019, this is a brilliant one to dig up and find. Basically goes through Paxos and breaks it down and just shows that, okay, well, Raft is just a special Paxos with a few things pinned down. And it was basically saying, pin down the things that you want to be, that are invariant in your system, and then you don't have to pay the tax to have consensus around those things. And so she's talking about this wide continuum of different flavors of Paxos, where things are wide open and very expensive, or locked down and less expensive. And then at a certain point, we realized, we don't even need a consensus algorithm. We can even go lighter weight than that. What we really need is just leader election. And so we looked at lots of different papers on leader election and the cheapest ones, and we found the bully algorithm was really cheap. And then we realized, okay, because we're on the Erlang VM and we have a cluster formed, there's some data that's already been agreed on just by the fact that we have a node connect that's happened. And so there's some information that's already been gossiped around, and it's already there, and we'll piggyback on that and have something even simpler than the bully algorithm. And so we basically built an internal super cheap, super fast, it's a gen state machine called Leftist Strongman, and it's very small and very quick, and has less communication cycles that you would have to have on even something as lightweight as the bully algorithm. And so this is one that might be a candidate for us to open source at some point. We'll need to peel out any of the specifics that we have, but it's a really nice lightweight library that was built off of this whole trajectory that we've been talking about here on. From Paxos to Raft to leader election, less than that, bully algorithm, less than that. And then again, similar to how on the earlier slide, the wheel reinvention, it's like we didn't really need this big wheel. We needed a tiny little wheel. And so we built that. We now don't have to maintain a big heavy wheel. All right, location transparency. And so this from the mailing list, Joe Armstrong says, basically sums up to however it works in the distributed case is how it should work locally. And so this is a super powerful idea on the Erlang VM. And this is one of the key reasons that Waterpark was built on the Beam. And so we got all these fault tolerance, high availability things, but we knew this is going to be a distributed system, and we want to have we want it to be transparent. Like the idea of, we don't need to care. We wanted this to be very cloud-like. And so a lot of things in the cloud aren't very cloud-like. A lot of aspects of Waterpark are. We don't really have to worry or care where a patient actor lives. The system basically takes care of that, and it just lives somewhere on the fabric. And we know that just off of the rules of the hash rings and so on, they're going to be separated in ways that mean we're going to be able to resist we're going to be able to take a punch, or if a server falls down, we're going to survive that. If a data center falls down, we're going to survive that. And so for location transparency and all the good that you get out of that on the Erlang VM, it's really good to build up on top of the Erlang VM and build some abstractions. And so in Waterpark, we have mailroom. And so we're going to extend this location transparency idea to the actor and level, and we will, so it actually is aware of our concept of actors. So here on the topology, each Waterpark, each node is a peer. And any node, we can send a message into any node. You don't have to know the node that this message should go to. It could go to any node. And if it lands over here and off of the topology, it says, okay, so no one on the outside needs to know or care about this. But the cluster hash rings and registries, et cetera, they do know about this. So each node has this mailroom, and the mailroom knows the topology, and inbound messages are routed through the mailroom to the appropriate patient actor. And so if the patient is remote up here, we're going to see that. And so the mailroom is going to route that message to the remote node's mailroom. Okay, all this thing was in flight. That message was going across. Say there's a topology change, and or it went to the wrong node, or that server died, or something's different. Something in the world shifted. The mailroom, when it lands on this server, it's the same as when it landed on the wrong server in Florida. It's going to say, "Oh, you're on the wrong server, buddy," and it's going to relocate it and route it to the correct one. And it goes over here to this server, and then we spin up our patient actor, and we get our admit message. Like we did before with the picture with the two beds. But here you get to see that happening on the cluster. And hopefully that visual helps bring some ideas together. Okay, so our mailroom, what it does is it gives us, outside of the ability of not having to worry or care about where something lives, it gives us some other nice things. It gives us a really nice seam for testing. And so when we're testing how things go from server to server, we don't have to spin up a cluster inside of our, we don't have to have these like integration tests, or these integration tests, that are these unit tests that are really integration tests. We don't have to have that. We can just mock out the mailroom, and then it creates this beautiful seam for testing. It's like, okay, all I have to know is that when this thing happened, it made a mailbox, like a mailroom call. Sure enough, it did. Assert that, good. Done. It gives us a place to bundle data. So we're sending all sorts of data across. Does it make sense for us to zip things, compress things? Does it make sense for us to take all the things for this one node and send those in packets over to somewhere, and bundled up packages over to some other node? Do we need whatever middlewares we need to insert? We can do things like compression or encryption. We can do monitoring and telemetry things, measuring all sorts of bits. And also it lets you hide the icky RPC bits or any sort of remote gen server calls or anything like that. So we never say gen server.call, other server name, comma, module function args. We never do that because too many things can go wrong. There's surface area there. And so with our mailroom, we limit that surface area and we control all the complexity there. And it also would give us a path. If we decided for whatever reason, we need to have this server talk to something that can't talk over distributed Erlang, well, we could replace that. We could have it talk over Morse code, or it could just be almost anything between there. We could talk, Phoenix channels to something over a front side and get across a lot of these ideas and do the same thing. And we wouldn't have to change anything about the mailroom. Alrighty. There's a thing that Joe Armstrong talked a lot about anytime you have a system, you to state your invariants, the things that are just the truth. And so this will, hopefully this won't be dull. Hopefully this will, this exercise in Bryan reading to you will be, it'll give you a more complete view of what Waterpark is and how the actors work. So every patient actor has a key. The facility of the patient is part of the patient actor's key. Every patient actor is registered by key on its local node's registry. It's Elixir registry. Every patient actor is supervised. The commands are delivered to a patient actor via the mailroom. If a patient actor is not running when a command is delivered, it will be started. If topology is changed and a patient actor's key no longer maps to its current node, it will migrate to the correct node. Every patient actor has one read-only follower process pair at each data center. A patient actor processes commands and emits events. So if you're familiar with CQRS or into that, then this should be familiar. Before event sourcing, before a patient actor commits an event to its event log, 2 of its 4 read-only followers must acknowledge receipt of the event. And so while we're eventually going to write to all of the ones out there, as soon as we get a majority back, we can go ahead and optimistically act and move on. When a patient actor starts, it will ask via mailroom if its 4 read-only followers have state. If they do, the patient actor will recover from the best reader. So if you remember that diagram earlier where Florida A2 crashed and the process was spun up on Florida A3, it would have reached out then to its read-only followers and said, hey, do you exist? And do you have state? And if you do, I'd like that state. That means I must have crashed. And so that's how it recovers. Each patient actor's state contains its key, an event store, and a map for event handler plugins to store projections. And so those are the kind of basic invariants that we have around our patient actors. Any questions there before we move to just kind of the closing bits? We have just a few bits around how we deploy and so on, but I want to stop there while we're still talking about actors, if anyone has anything.
I have one.
Yeah.
It's about just sort of your general strategy of how you prevent bad state from getting like persisted across the network or things getting caught in crash loops.
Yeah. So if a message comes in and that message is poison, is that what you're basically saying? There's a poison message or there's a message that triggers a bug?
Sure. Yes.
Okay.
I think hard poison is usually easier to solve for. It's kind of the slow poison that's always the most insidious.
Yeah. So if you had, so we have a patient that's up and it's had 100 messages on it, and someone sends the poison message to it, it would go through and it would run all of its event handlers and actually it wouldn't crash the process in the sense, well, it depends, because generally the patient actor doesn't itself care too much about, so it would really have to be a pretty exceptionally poisoned message for it for the actor to care about it itself, because the actor itself doesn't think so much about the messages. It basically has a series of these event handler plugins here that we're going to talk about in just a bit that handle the messages. And what they're going to do is each one of those event handler plugins, if the poison basically triggers a problem in one of those, that event handler will fail. And so basically that event handler will error out, it will log, and basically the knowledge that that event handler was going to try to infer from the message, it won't be able to because it triggered a bug or whatever. And so that part just fails. And so in the entire system of Waterpark, actually in my entire career, since I bumped into Erlang in 2007, the first time I ever wrote try in code and had a try block inside of any Elixir or Erlang system was, and there's actually, I think there might only be 2 places in the entire Waterpark code base where there's try, or this is the main one right here, is around basically as we handle these messages coming in and we go through an enum reduce across each of the event handlers and give each one of them a chance to process a message. And so if any one of those crash, we want to catch the error. We don't want the actor to die, and we just handle that, and it gets logged. And then the other event handlers that can deal with that message work. And if none of them, if they all crash, then basically the state isn't mutated. And if you come back with errors like that, then you would knack the message that came in, and of course they could keep on trying. I guess they could be jerks and, and just keep on sending the same message back at you. But the good thing is that's you've got someone sending a bad message to that patient, and if they keep on retrying, it's going to be to that one patient, and that cycle would play out. But it's only getting its scheduler slice of the core on that one machine, and so it ends up not really being a problem. If we had something that crashed a process or crashed one of our actors because we were trying to inspect something, the patient actors, they don't really think too much about the messages themselves. They hand that off to these basically this extendable plugins. But say if one did, and it did crash, what would happen is that process would crash, the sender would get a knack for basically the command handler that took that message from the outside and then relayed it on to our patient actor. That crash would be interpreted as an error and would return a knack back to the sender of that message. And then what would happen is that patient actor would respawn, and it would say, "Hey, I'm a brand new patient actor. Do I have any buddies out on my other?" And it would recover its state from the other readers.
True. So that most recent like poisonous event would not get,
Yeah,
as I understand, committed to its log.
Yeah.
So does that state just get dropped on the floor then at that point, or
the state was never committed, and it
Right.
was knacked. It was knacked back to the sender of it, and
Gotcha.
and so if they want to keep on being jerks and keep on sending it, they I
pushes
guess
it back to the edge?
yeah,
I gotcha.
yeah. Does that help?
Yeah, that's super helpful. Thank you for
Cool.
unpacking that.
Yeah, and as we can talk about all sorts of design things, and there'll be a little bit more here as we go into the event handler plugins, and maybe there'll be more questions there. But I'm just tickled to talk through any of the details that y'all are interested in. So let's see. Deployments. So we went to production in April of 2020, and since then we've had like 1,000 builds that have been deployed to the cluster. Not every build gets deployed as its own deployment, but a lot of them do. And so we've had but we have different ways of actually deploying to the cluster. And so we have full-on Erlang OTP releases. Our build system, when something gets PR'd, reviewed, and it's passed all of its tests and it's passed all of its checks and so on, and it's merged, we create a release, and that release gets automatically deployed to our dev cluster. It gets deployed to our QA cluster, and then a release is ready for us to then deploy to our prod environment. So that's the way a lot of releases go out. We also do hot code loading, but we don't use OTP releases, and we don't hot code load OTP releases. What we're doing is actually doing beam shipping, and we will update particular modules. And so that's we do a lot of that. We do more releases, I'd say for every maybe we do a hot code load for maybe every 5 releases or so would be our ratio. And so, but we've done hundreds of releases since we went to prod on this running cluster that can never go down. And so we also do dark launches of things, and we have our universal servers and plugins is how we deploy. And so we'll talk about that in just a second too. So our OTP releases are kind of as you'd expect. They're just rolling deployments. And these are not far from being chaos testing, because we have our cluster there and we are basically deploying, and those 4 servers might as well have had the power yanked on them. And then when they come back, they're running the new release, and they get their brains from their buddies that are still up. And so so we are testing our fault tolerance capabilities with every single release that we go across, that we roll across the cluster. And yep. and so it's brutal, but it keeps us honest. And the hot code loading is another route. And so if y'all are not familiar with hot code loading, well, you would be familiar, because every time you, even if you're in like testing a Phoenix app locally or something and you save, well, those modules are being built automatically underneath you, and then the new code is being loaded out. But if you've never done this, if you have a cluster, a little local dev cluster set up, and you compile some file on one node and you need it to be on your whole cluster, you can go into an IEX shell and you say NL of the module, and it will load that code across all the nodes. And so that it'll ship the beam basically. And so the same code that happens whenever you do a node load, those primitives of where you're shipping a beam out, that's what we're piggybacking off of, these low-level primitives. And this kind of goes back to earlier, as we were talking about the low-level primitives of links and monitors. Well, that's how supervision is built. Well, we're building on these low-level primitives of how the code loader works to basically do a thing that has enabled us to be up. And so it allows us to change the tires on the car while it's driving down the road. But so this example here, so you have 4 modules out, and you've got 3 processes running code that's in those 4 different modules. You know, if you rebuild and push that 3rd module down, you saw that sort of blink that happened there. And these guys, they all reload, and the next external call into a function on that module, it will reload. It will, so if you can have 2 versions of a beam on your cluster or on a server. So if you've got your calculator module out there, and you've built a beam off of it, and you make a change and you load that across, you reload that beam, or you recompile that beam, or you ship that beam to your other servers, what's going to happen is the code loader is going to say, okay, I've got 2 versions in here. I can have it one time. I've got anything that's in a tight loop over here running this one. And the first external call, so the first module function args call that happens to this thing, I will load this thing in, and this code will keep on running. There's no shutting down the process. There's no killing the process. It's just straight in line, and it loads in, and it's it's spooky magic and awesome. Also, it's a sharp knife. So you need to be aware of what you're doing, but this is what it looks like whenever we deploy. So when we deploy the releases across the cluster, that's a process that maybe takes a couple of hours for it to roll across, because we don't move on to the next wave of servers until we fully heal the previous wave. And so, and all that data sloshing across the network and so on. But here, since we're not actually downing the nodes, it looks more like this. So we say patch, and we have a date of the patch that we've just created. And we say deploy this patch, and blink. Everyone gets the new code, and the code keeps on running, and the next external call into that, the whole system is updated like in a second for the new patch. And so that looks a little like this, where we say push this module to this node, and here's the module you're going to push out there, and it says, okay, get object code of the module. And we pin against the module to make sure it's the same module. And then here's the binary, and then the beam path. And then we are basically shipping that over to our other node and saying, okay, on that other node, code, load library, module, function args, so module, beam path, and bin. And at the point that happens, that code is then deployed on the other side and loaded in, and the next external call is automatically going to run the new code. So powerful, sharp tool, and using the primitives directly. So we generally limit our hot code loads to, not that we'd have to, but we generally load in plugins and stateless modules. You can load in gen servers. You have a few more places you could get yourself hurt, though. And we have done hot code loading on gen servers, but we tend to do it on our on helper libraries and pure modules with pure functions on them. And then we have dark launches, which means we've basically pushed out a feature in a release that's basically latent. It's just turned off. And then we will do basically a call to then update the environment and basically turn a feature on. And so hopefully the idea is clear there. And so what that allows us to do is if there's something in a release that is very complex and we're going to roll it out and it has lots of stateful things, and we feel more confident of pushing out a release with the bouncing strategy, we have that thing out there. It takes it many hours for it to happen. And but all the features inside of that thing are doing nothing up until we do the 1 second call here of saying deploy the environment, put the application put in to flip the feature on. Alrighty. So there's an idea that Joe Armstrong put out, is like his universal server. It's a blog post, and he basically talks about this idea of his favorite Erlang program was to have a server, and it does nothing. It just takes a function, and it basically is in a tail loop, and then it will receive if you call into it and pass a function into it. And if you pass in this function, it will run that function, and so it's just going to tail loop. And so you can take a server that's a do nothing server and then push code to it that makes it an HTTP server or an FTP server or so on. And you can a really fun experiment, and this would be a good show and tell for any Elixir group, is to basically build like a MUD or something, basically, or any sort of game loop where you start off with a gen server that does nothing. And then, or it doesn't even have to be a gen server. It can just be a process that's doing a loop, has a tail call of loop. And then you just do a series of node loads or recompiles and add functionality into your running server. And so you can start adding it where you can handle move lefts and move rights and do things like this, and it'll update its state. And so, but anyway, that's a really fun project, and that'll sort of break people's brains. They're coming from other stacks. But so this idea, we use this idea of the universal server, and this is what we call our event handler plugins. And so as COVID hit and Waterpark, we went into production, we knew we needed a way to turn the patient actor into this universal server that could be extended and changed dynamically at runtime and have no downtime. And so this is what we did in that 3 weeks. Earlier we had the slide that said in 3 weeks you got to go, you can never take downtime again. We didn't shore up other things. This is what we added in. We added the ability of being able to push these plugins out. And so in 3 weeks, we implemented our plugin system and applied it to the running cluster. So here up at the top, we have our patient actor. And, as we mentioned in the invariance part, each actor has its key, has its projections. Basically, the projections are its inferred knowledge. And so each of these handlers that are running, they're going to be able to process messages, and anything that they glean, anything that they learn from these messages, they're going to put into projections. And so each event handler is going to have a key within the projections, and it's going to own that key, and it's going to be able to update state and basically put all the knowledge that's learned off of that latest message. And it also has an event store out there, which basically has the history of all the messages that have played before. So if you needed to do a time machine and roll back to something in the past and and then make a better future based on your going through your time machine and playing things forward, you can do that as well. And so we got this infinite stream of messages passing through the patient actor. And so we then have these, when we boot up, we load all of these event handler plugins, and we can dynamically load these through hot code loading as well and push these out. And these plugins, they all have a contract. And so the contract, basically, this is sort of pseudocode for what they're doing, but they can basically handle a message. They're given the current projections of the patient actor. They're given the key of this patient actor. They're given the message that's coming in, and then they're given that event store of messages that have been applied before and have been replicated and so on and been act. And then each one of those handles then returns an OK, and then its map of its updated projections, like the projections as they came in, plus any inferred knowledge. And so since these plugins, this gives us a place to add all this this business logic without affecting the core of the platform. And so all of the messy business, high surface area stuff gets put into these pure functions inside of these plugins. And since the plugins are all pure, it becomes a really nice place to put property-based tests in. And so you can think about all the scenarios, blast. And so we have property-based tests around some of the trickier business logic plugins, especially when we have lots of date things that happen. That becomes a really excellent place for property-based tests. Complex rules. And so these rules inside of this, we can define these rules as basically a checklist. And so let's see, yeah, here I had the book. So I don't know if y'all are familiar with Atul Gawande's checklist manifesto, but this book is really nice. Not a programming book at all, but basically talks through the idea of checklists and about how you can improve outcomes and so on, and basically how they're used in airlines and in surgeries and so on. But what we do in a lot of the handlers is we have a series of checklists, and we'll see that more concretely in just a second. So up to now in the talk, it's been a whole big bunch of how, and here we're going to talk about why it matters. And so one of the first things that we implemented in Waterpark that was important, so we knew we were going to be helping in the response, but early in the pandemic, we developed a patient actor plugin that was going to immediately notify facility caseworkers anytime a patient who had transferred from a long-term care or skilled nursing facility, if they transferred in from a facility like that, and then they tested positive for COVID. And so what this was allowed was then early contact tracing, and it allowed the caseworker to call that skilled nursing facility, that long-term care facility, and let them know, because they just might not have a clue that they had a patient that transferred in. They weren't sure whether they were sick. They knew they were sick, and let them know, because that way they could do contact tracing and quarantines at the facilities. And this would reduce this virus spread within these extremely vulnerable communities. And that was tough stuff that hit a lot of us, I think, really close. I think we can, probably everyone on the call has a story not far from this. And so here's the simplified rules of that particular alert. So, is it admission source, nursing home, or long-term care? Is there a COVID lab order for this patient? Do we have a result for a thing that was a COVID lab order? And was the result that tied back to that COVID lab order positive? And have we already notified the case manager? So comes through, we find out, sure enough, admission. And so this would change at the EMRs actually as well, and facility by facility, the way you would actually infer this knowledge is different. And so this handler would go across the different EMRs and look for the values in different places based on the EMR and say, yep, this is skilled nursing. And at different facilities, maybe those codes were different, and so on. Is there a COVID lab order? And this varies, facility by facility, EMR by EMR. These basically the codes that would represent COVID-19 lab orders. And of course, you're talking about a lab test that didn't exist, just a little bit before. And so the idea of standardizing everything across these different EMRs wasn't going to happen. And we were able to do that though in the handlers, and basically have these crosswalks and these mappings, and then infer, and then have a very simple thing to be able to say, yep, it is a COVID-19 lab order. And do we have a result? And based off of that EMR's codes and so on, that maps to being a positive for COVID. And we have not, in fact, informed the case manager yet. So we're going to send that out to the case manager. And then we're going to say, yes, we have informed the case manager, so that they don't get alerted over and over for the same patient. And so this one, all these ideas, that built in here. We've seen Joe's face on here a whole lot, but so he passed away in April 2019, and about a year later, his ideas that had informed this whole platform, they're out there making nursing homes throughout the whole country safer than they would have been otherwise. And I just think that's it's just a beautiful, beautiful thing. Just owe him so much. So here's I got a chance for my whole family to hang out and play with Joe back a few years back, and you got to know him over the years, and I'm really thankful for that, and just so much wisdom there in that whole crew. And as we've been talking through the whole talk, papers we love, there's just so much good out there. There's so much to be mined. If you noticed, we're not building on the hottest tech that's sold by vendor XYZ. Most of this stuff has been built by our little team. It's been a lot of DIY, and it's all built on knowledge from characters like Joe, and all the way from the actor model slide, and then on through the bloom filters and so on. All these folks that have contributed out there, and so standing on the shoulders of giants for sure. So I'd say observe papers and conference talks, pursue long ideas. And so the idea of Waterpark, so I'd had a tour at a hospital company back in the late 90s and early aughts. And if any of you have ever played the game Zork, the character basic game, there's this one scene in it where there's this egg that you can find, and you try to open the thing. It says, "You have neither the tools nor the expertise," is the sort of taunt that Zork gives you when you try to open the egg. And that's what I felt like back in the 90s and early aughts, is I had neither the tools nor the expertise to actually do important work and to do anything good when I was working at this hospital in this IT back in the 90s and early aughts. And it was frustrating because I knew that this was a space where important work could happen, but the tools were really terrible. And then I was also, I didn't know a lot. And so I tried to learn a lot because I wanted to be able to do something good and useful. And out of just pure dumb chance, I ran into Erlang back in 2007, and click, I started realizing really quickly that this would have helped me with some of the problems that I was looking about how to solve back in the 90s and early aughts. And that haunted me that I had this knowledge now, I had these tools and starting to build expertise. And so I started thinking about this problem of my family at hospitals, different people, and just knowing about the things that were missing there that the Erlang VM could provide. And so I started really thinking about this idea of the patient actor. And when the CQRS was first introduced by Udi DeHaan and Greg Young, those ideas immediately got folded into my new Erlang. So this is like, I'd been playing with Erlang about 3 years then, and those ideas got folded in. And so I started cooking around this idea of the patient actor, and started creating models of this. And then that turned into being able to present that to folks that had a place for it. And that's how that whole thing of given the Erlang VM and all the data, what good can we do? So this was an idea that had been cooking for a decade, 2 decades. And so pursuing long ideas, I think, is, keep being haunted by things and keep on thinking about, just because it didn't work out then, don't worry about the technology around it and the whole landscape that's shifting around, I guess, is an idea. And over and over, we get told, it's almost, we're shamed into not rewriting things because it already exists out there. And, if exactly the thing you need is out there, then use it. But if that thing is you're using it because it's a resume bullet, or you're using it because it's the hip thing and that's what people are doing, and you don't feel the confidence to push back against it, you might be taking on all sorts of dependencies and all sorts of, you might be polluting your design. And so I don't, there's a lot of really great architecture and a lot of great thought put into the Apache projects. But there's also a lot of sadness when you see a bunch of Apache projects just glued together. And like, it's just this monstrosity of this stuff, and they all have slightly different, anyway. Yeah, so there's that. So reinvent some wheels. And then look out for, you know, places where you can create work that's meaningful, find or create it. And, we get so many years on Earth, and it's awfully easy to spend a career doing things that that don't give you the chills, that you're not really that proud of. It's just like you went from thing to thing to thing. And we're in a field where there is important, interesting stuff out there. And it's just takes a little bit of going out on a limb to find it, and taking those chances. But that is the talk.
Awesome, Brian.
And yeah, so
that.
yeah, thank you all, and a big thanks to all the crew back at HCA. And one of them is here, Paxton. He's on the Waterpark team, and
Oh boy.
we got a good bunch. And I'm it's building this whole project. It's been the most fun, meaningful work of my career, and so I'm thankful to them. It's just a brilliant crew, and yeah. And here's contact info.
Perfect.
And if you wanted to be colleague 275,001, reach out to me. And as soon as there are spots open, if you want to just keep in touch and say, hey, I'd like to be part of that. Reach out, and then as soon as things are open, things open up like every month or so. There'll be some new team doing some cool thing. So reach out. And so that is the talk, and I'll go ahead and I can stop sharing, or if people wanted me to go to a particular slide, or
does anyone need to look at a slide? Because I was actually going to say we've kind of run over, so I was going to wrap it up here. But if you wanted to hang and chat to Brian, I would encourage you. Otherwise, I'm assuming we could either email you or reach out to you.
Oh yeah, absolutely, yeah.
Okay.
Okay, I will go ahead and stop the share, and we can just chat if
that's great. Then I will also stop the recording because it's so obvious. No, it isn't. What the hell is it? Recording.